Hi, everyone. In this lesson, we're going to continue with Chapter 4, and we're going to cover Section 4.3, the coefficient of linear correlation. So in the previous section, we covered scatter diagrams, and we went through the different types of correlations that may be seen when we look at a scatter diagram, such as a positive linear correlation or a negative linear correlation, or even no linear correlation. And then I talked a little bit about strength. I did that example on the whiteboard where I presented you with two different scatter diagrams, A and B, and we compared them. They both indicated a positive linear correlation, but one of them was stronger. So remember what I said in that last lecture, that the more closely the points in a scatter plot approximate a straight line pattern, the stronger the relationship. Now, we have a measure that tells us about the strength of a relationship. So when a scatter diagram seems to indicate that there is a linear correlation between two variables, what our next step is to measure the strength of the relationship between the two variables. And we do this by calculating what's called Pearson's correlation coefficient, and we use the letter R as the symbol to represent the correlation coefficient. So here's the formula for calculating the correlation coefficient. And in this lecture, we're not going to calculate the value of R yet. I'm just going to show you how to interpret it. And then in the next lesson, we'll use the calculator and I'll show you how to calculate the Pearson's correlation coefficient R. But this is the formula. And I do want to talk briefly about the formula because even though it looks, a little intimidating, once I break it down, you're going to realize that it's really not so bad. So if we look at the numerator, you see how we're taking the sum of the product of each x value minus the mean of all the x values times each y value minus the mean of all the y values. And then we're going to divide by the sample size minus 1, and then we multiply that by s sub x. It represents the sample standard deviation for the x variable. And then S with a little sub y represents the sample standard deviation for the other variable, for y. But if you look closely, for example, look at this piece that I'm highlighting right here. You see how we have x minus x bar over s sub x bar, and then we multiply that by y minus y bar over the standard deviation of all the y values. When you look at it like this, these two formulas should look very, very familiar, right? Doesn't this remind you of Chapter 3? This is your formula for a z-score, isn't it? Data value minus the mean over the standard deviation. So that's essentially what we're doing here. We're summing up the products of the z-scores for each data value in the x data set and each y value in the y data set. And then we're dividing out by sample size minus 1. So we're essentially taking a mean. And this value, the R, Pearson's correlation coefficient, this we use as a measure of strength for the linear relationship between the two variables. And I'm going to show you how to use the calculator to calculate this in the next lesson. For now, let's just talk about the characteristics of R and how we interpret it. So R always has to be a numerical value between -1 and +1. So the smallest that R could be is -1. The largest value that R could be is +1. And I think this figure below is a nice illustration as to how to interpret the R value. So we said, okay, R could range anywhere from -1 to +1, with R equals 0 being right in the center. And I think R equals 0 is kind of the easiest to interpret because remember, R is measuring the strength of a linear relationship. And if R is equal to 0, that means that there is no strength. There's no linear correlation. So if R is equal to 0, that indicates to us there's no linear correlation. However, as R gets closer and closer and closer to +1, so if R is a positive value, there's going to be a positive correlation. But depending on what the value is, it may be weak, moderate, or strong. So the closer that R is to 0, the weaker the relationship. The closer to +1, the stronger the linear relationship. And if R is equal to +1, that's a perfect positive linear correlation. So what do you think the graph would look like? What do you think the scatter diagram would look like if X and Y had a perfect linear correlation? If you're thinking a line, a perfect line, you're right. So let me give you an example. If we had something like this, and I'm just drawing this freehand, but I'm trying to make these all on the same line. So this would be an example of a perfect positive linear correlation where all the points line up perfectly on a straight line. That's the strongest possible positive linear correlation. And then we could have anything in between 0 and +1. But we could also have a really, really strong negative linear correlation. So just because R is negative, it doesn't mean that there's no correlation. All that means is that there's a negative correlation. And the closer R is to -1, the stronger the negative correlation. So again, the closer that R is to 0, the weaker the relationship. So now you could probably guess what a perfect negative correlation would look like. That would be a perfect negative line, right? All the points would be lined up perfectly on a negative line, and that would be a perfect negative linear correlation. So this would be an example of the strongest negative linear correlation that's possible. And then, like I said, we have everything in between. But the key is the closer the R value is to 0, the weaker the relationship. The closer the R value is to 1 or -1, the stronger the linear relationship. So let's do 2 examples. I think the next 2 examples are going to get you more comfortable with how to interpret R. So we'll get back to oh no, this is still more on, so we'll talk about this, more on the relationship between the correlation coefficient and the scatter diagram, interpreting the values of R. And this is a nice summary, these 3 bullets of what I just said to you above. So everything that I kind of explained when we were looking at this diagram right here is summarized very nicely for you here. So the first bullet says, a value of R equals 1 represents the strongest positive linear correlation that's possible, and it indicates a perfect positive linear correlation. A value of R equals -1, we said, represents the strongest negative linear correlation, and that would indicate a perfect negative linear correlation. And then we also said a value of R equals 0 represents no linear correlation between the 2 variables. So let's keep all that in mind, and let's look at example 3. I think example 3 is a nice example. So what we have to do here is I gave you 6 R values. So 6 values of Pearson's correlation coefficient R. And what we have to do is match them with the appropriate scatter diagram below. So, I mean, there's no right or wrong way to approach this. Typically, what I do is I like to go through the scatter diagrams and just say if they seem to be positive, negative, or no linear correlation, and then I'll go and match them. So, for example, like if we look at scatter diagram A, there's definitely a positive, right, linear relationship. If we look at B, there also seems to be a positive linear relationship. If we look at C, there also seems to be a positive linear relationship. It's definitely weaker than the first 2, but it seems positive. And then if we look at D, I'm seeing a negative relationship. E doesn't seem to be positive or negative, right? I can't imagine fitting a positive or a negative line through there. They're too scattered. So I'm going to say no linear relationship. And then F definitely also is negative. So this is just going to help me know what sign my R value should be. So if I have a positive linear correlation, R is going to be positive. If I have a negative linear correlation, R is going to be negative. So I'm just going to start with the positive ones. Let's look at the positive R values. We have R is equal to 0.48, R is equal to 0.80, R is equal to 0.95. Those are the positive R values. Now we need to match them appropriately to the positive scatter diagrams below. So remember, the stronger the relationship, the more closely the points will be to a straight line pattern. So between A, B, and C, A seems to have the strongest linear relationship. So that's going to have the R value that's closest to 1. Because remember, the closer we are to positive 1, the stronger the relationship. And that's going to be this R value of 0.95. So I'm going to assign the R value of 0.95 to graph A. So now we can cross that one off the list. We're not going to use it again. So now I have 2 more positive scatter diagrams, and I have 2 more positive choices for R. Now, between B and C, B seems to be the stronger relationship, right? Because the points more closely resemble a straight line pattern. So we're going to pick the R value that's closer to positive 1, and that's going to be 0.80. So now we could cross that R value off the list. And then there's only one positive graph left and one positive R value, which is R is equal to 0.48. So we could cross that one off the list as well. Now we could go to the negative R values, and there's 2 negative graphs and there's 2 negative R values. Determine which of the 2 negative scatter plots has a stronger relationship, and that's going to be F. You see in F, these more closely resemble a straight line pattern. So we need to pick the R value that's closest to -1. That's further away from 0 on a number line, because 0 means weaker. So out of the 2 choices, R equals -0.85 is going to be the stronger R value. It implies a stronger negative linear relationship because it's closer to -1. And then by process of elimination, the R value for graph D, which has a negative relationship, is going to be -0.57. So we could cross that one off the list. And then there's only one graph left, which seems to have no linear correlation. And the only R value that's left, which makes sense, is an R value of 0, which implies no linear correlation. So I think this is a nice example, and it's helpful because it helps us practice interpreting R and relating R to different scatter plots. So let's do one more example and then we'll wrap up this lesson. Let's look at example 4. So what I want you to do in example 4 is I want you to rank the following values of the correlation coefficient R from strongest to weakest. So I gave you 7 R values, and we want to put them in order, not numeric order, but order from strongest to weakest. So the stronger the correlation, that means that R is going to be closer to either -1 or +1. The weaker the correlation, R is going to be closer to 0. So we're not even looking, we don't even need to look at the positive or the negative values in front of these numbers, really. We could ignore that. What we want to do is the numbers that are closest to 1, whether it's -1 or +1, are going to be the strongest, right? So look at this -1. That's going to be the strongest association. That's as strong as we could get in terms of a negative correlation. Next, well, what number do we have next that would be closest to -1 or +1? And that's going to be 0.95. So we could cross that one off. Next, again, I'm ignoring the positive and the negative values. We're just looking for numbers that are closest to 1. So now out of the numbers that are left, the one that would be closest to 1 is going to be the negative 0.83. It just happens to be closer to -1. We could cross that off. Next, we would have 0.50. Then we would have 0.25. So see how now the weaker we're getting, the closer to 0, right? Then we're going to have negative 0.10. And then the weakest R value here is going to be 0, right? That indicates no linear correlation. So this would be Pearson's correlation coefficient R, these R values ranked from strongest to weakest. So again, we really just care about the absolute value. We're not even looking at the positive or the negative sign. And then we could list them in decreasing order down from the strongest to the weakest linear association. So that wraps up this lesson. In the next lesson, we'll start section 4.5.